Hello, welcome to the course again. So what we do is we continue with what we have been talking about, the design of shell and tube heat exchangers, and we are having a general overview on the topic. We start with the same step or the same point which what we discussed earlier, like the basic design steps. While you design any shell and tube heat exchanger, the first step is evaluation of the heat load Q. When you evaluate the heat load Q, you normally will be knowing at least either the heat load or at least two of the temperatures and the flow rate and naturally the physical properties of the two fluids. That means by the end of this, you will have your 4 temperatures known to you. That means both the in and the outlet temperatures are known. The next step is a preliminary selection of the heat exchanger type, whether it is a double pipe or it is a shell and tube, or if it is a shell and tube, what type of it is. We make a educated guess, mostly based on our past experience with similar systems. We have a rough estimate of the overall heat transfer coefficient U after that, and then what we do is we go for evaluating it in more details. Once we have estimated U, quite naturally the basic equation of heat balance Q is equal to U A delta T effective. Since we know all the temperatures and the exchanger configuration, we know this, we know U, we know Q. So, we have an estimate of A. So, once we have estimated A, we have to realize it, and that is the design part of your double pipe or shell and tube exchanger. You design for providing this A in reality and then verify validity of all the assumptions you have made so far in arriving at it. Now, one thing I did not speak in the last class, that is very often in the classical design step, there is a term which is called heat release curve, which we will be learning in more details later on when you talk about heat exchanger network analysis. But you often see this curve in the calculations provided by vendors. You have, if you have a fluid which is getting cooled from a temperature T1 to a final temperature T2, it is cooling. Then what you do is you start with the temperature T1 here, and if you reduce the temperature by a particular amount, what happens is you get some heat released from that particular stream. So, naturally these Q will be kilojoule per kg of the fluid. If it is a superheated vapor, say if it is a superheated vapor, you will be initially losing the superheat, that is definitely the sensible heat of the vapor. Then what you have is you keep on losing at the constant temperature the latent heat, and once everything has become liquid, if you cool it further by removal of heat, it will be the sensible heat of the liquid. So, from here to here the change is due to the presence of vapor plus liquid. Here it is liquid and in this zone it is vapor. Suppose this gives us a very big advantage. If I am going to design a de-superheater condenser, that means what enters at a temperature T1, we know from this curve that how much will be the quantity of heat removed in de-superheating, how much will be the heat removed during condensation, and if you have a subcooling, what will be the quantity of heat removed during the subcooling of the liquid. That means you will have 3 components Q1, Q2 and Q3, and your total load will be the sum total of this per kg of your fluid. This clearly tells you about something. It makes your calculations much easier for designing, as you consider in such heat exchangers 3 different zones of heat transfer, and then you go for your design. This I have just told you because you may love to have this in hand before you start your design work, particularly if you are going to have phase changes. I have one question for you. What I have drawn here is basically for a pure component. And how do you know it's a pure component? It's pure component because the lambda, or the heat of the latent heat, is removed at a constant temperature of condensation, and it is obvious this is drawn at a constant P. If it is a mixture of components, you will have a shape something like this. It will be T here, the vapor above the vapor above the bubble point. You have a stream like this, the line will be something like this, then you have a bend, and then you have, that means the removal of the vapor and the liquid is not over a constant temperature when you have more than one component in your mixture. And this basically is the point of condensation, which is the bubble point, which is the dew point, and this temperature is the bubble point of your component at constant pressure. This is very common with hydrocarbon systems, and it is there in case of many other systems, and this helps you in designing exchangers more with phase change. We come back to the old design. So, what we do is we know the components now. What we have here is a 1-1 shell and tube exchanger, and what we have here is a 2-4 shell and tube exchanger. And we also know that such services could be definitely with different multipass configurations, and quite naturally one fluid will be hotter than the one fluid will be getting heated, the other fluid will be getting cold, the hot and the cold streams. And in case of multipass and in case of single pass, there are typical standard configurations which allow the entry and exit to be there. Here you will see that in case of a counter flow and a co-current flow, the matter is simple. Usually you will have the cold fluid inlet here in the tubes, typically coming out through this, it enters here and it exits here. The shell fluid will enter from the top and it will come here from the bottom. In case of co-current, both will enter from here at the bottom and exit from the top. In case of this, what you have is a 1-2 exchanger, and what you have here is basically the tube side, the hot fluid entry is from here, it goes like this, comes out through this, and your cold side entry is through the shell bottom nozzle, and it comes out through this. We will not go into the details because these are basically configurations, and you can refer to this particular diagram whenever you are going to design your heat exchanger. Now, if you look at a typical exchanger installation, well, the exchanger is not just the piece of equipment that you are going to design. You are going to design a heat exchange system. That means you have to design things around the exchanger also. The exchanger is, as shown here, is only this. Naturally, the tube side fluid comes here from the left, it leaves from the right, and you have a shell side fluid which is coming from this end and it is leaving here. So, this is basically the tube side fluid which comes in, it goes out, the shell side fluid comes in here and it goes out. You will notice one thing, that it is not just that there is only one entry and one exit, there are other piping involved also. Let us look and try to justify why these pipings are provided. You will notice that you have valves. The valves are used for either on-off condition or shut-open condition, or they are for regulations. The regulatory valves are the globe valves with these symbols. The valves which are used for full open and full close conditions are the gate valves, and these are the gate valves. That means here you have 4 numbers of gate valves and 2 numbers of regulatory valves, which are the globe valves as shown here, V6 and V5. Now, what happens is, if you would like to have a bypass of your tube side stream, what you will be doing is you have to open this. That means these are for regulating the bypass across the exchanger. When this may be required? When I would like to have continuation of this tube side fluid flow, but my exchanger is decommissioned, it is not in use. In that case, I will shut this, I will shut this, I will shut this, I will shut this, open this, bypass it and continue my flow here. The same thing is true in case of the shell side fluid also. For bypassing the shell side fluid, you have the globe valve set in here, and when you bypass, naturally you have to shut V3 and V4. Now, there is one thing which is new to you, which we have not talked about. I have mentioned here SV, which stands for a safety valve, and within bracket I have put here TSV, which stands for thermal safety valve. These things we will detail later on, but we will see why this is required. A safety valve is basically to release overpressure. You will notice when it releases, the release is through this particular path. That means, if I have overpressure at this particular point, some amount of liquid will be flowing through the safety valve depending on its setting, and it will come here, and in the process it will get depressurized, or rather the pressure will get released. Now, let us see when this may happen. This happens, and this facility is provided when there is chance of overpressure. It is not just a common overpressure, because what can happen is, if you have this valve shut, and if you have this valve open, and if you have this valve open, and if this is a hot fluid, possibly a hot liquid, the liquid which is cooped up between these two valves will get heated and it will expand. The expansion of liquid is always much larger compared to the metals. So, you will have an overpressure here, or the pressure inside will keep on increasing. So, in order to release this pressure so that it does not damage your equipment mechanically, this safety valve allows a passage of the overpressure liquid and reduces the pressure. So, I believe you now get that why such safety valves are called thermal safety valves also. Remember that thermal safety valves do not have any relationship with thermal actuation of the safety valve. No, it does not. It is not like a pressure cooker safety valve. It is just a common safety valve which is used for releasing the overpressure due to thermal changes. So, we know now what exactly is the purpose of a thermal safety valve and why it is provided in typical heat exchanger installations. In the last slide, what we have seen various multi-pass and single pass installations, and each of these installations will have these details of valves, and possibly as required you may have the thermal safety valve arrangement as well. Now, we come to a very important part of this topic. We are aware that Bureau of Indian Standard IS 4503 is the standard for shell and tube exchangers in India, and almost the world over the Tubular Exchanger Manufacturers Association, which is the TEMA, they have the standards for their exchangers. Now, we already know that any exchanger will have a stationary head. A stationary head will definitely have the stationary head connected to the shell. It will have the rear end and it will have the shell. Now, depending on the type of these three, both BIS and TEMA, they have classified the exchangers, and here is the classification diagram. You can see here the front end of the stationary head could be this type, A type, B type, C type, N type or D type. Let us look at similarly you can have E, F, G, H, J, K and X type for the shell. The rear end could be similarly L, M, N, P, S, T, U and W. So, what you do is whenever you see a specification being stated as AEW, immediately you will be referring to this and say that this is a type of stationary head I have, this is the type of the shell I have, and here I have an externally sealed floating tube sheet. That means it is for a high pressure and high thermal stress service. We just have a look at these classifications once more. The front end here, you have a channel and a removable cover. The removable cover is this one, it is bolted, and you have a split, a channel splitter here. The same thing is true, but here in this case you have the integral bonnet. You will notice here that you do not have a removable cover, it is an integral bonnet. So, if I have to remove, I have to remove the entire channel itself. The bonnet is integral with the cover. In this case what we have, the channel is integral with the tube sheet. You will notice something, this is your tube sheet in which the tubes come and end. So, you have this channel integral. So, this and this they are built together and you have an external removable cover. In case of N, what you do? You have channel integral with a tube sheet and removable cover. So, basically what you have is this, which is slightly different from C and N. So, I would like to know from you to go through these two and compare and find out what are the exact differences and where do they differ. Next, what I have is a special high pressure closure. So, this is definitely for a high pressure system. Now, we look at the shells. This one pass shell is the simplest. That means you have the two shell nozzles, one here and the second one here. The F type is a two pass shell. So, you have a pass partition in the shell itself. The fluid flow will be this way, either from the left to right, here and here, or it could be the other way also depending on the design that you have. But you have a longitudinal baffle. So, whenever you have F in the middle, you know that it is a two pass shell with a longitudinal baffle. If you ever find that your shell side fluid pressure drop is large, possibly what you would like to do is you would like to split the flow. So, the fluid in the shell will come here, get split here, come here and go out, and this will reduce your pressure drop. Why will it reduce your pressure drop? If you look at the pressure drop equation, delta P is proportional to the flow rate square, or rather the velocity square. If you halve the velocity, the pressure drop is supposed to be 1/4. So, if you make these additions and approximately you will see your split flow will lead to a lower pressure drop. You can have a single split flow or a double split flow. You can have a divided flow as well. Divided flow is very often used when you have a liquid coming in here, a liquid coming in here and a vapor leaving from the top. The same thing you can see in this kettle type of reboiler as well. The vapor leaves from the top, there are two liquid connections here. Now, you can have a cross flow shell as well, but cross flow shells are rather less popular. because your thermal efficiency in such case will be pretty low. Now we look at the rear end covers. The simplest is a U-tube bundle, or you can have a fixed tube sheet here with a rear end fitted onto it with a removable cover. It is very similar to the A-type stationary head. You can have other types also, but most of these like pull through floating head or a floating head with a backing device, and these are usually for slightly high pressure systems. Now once you have decided the type of exchanger that you need according to TEMA or BAS code IS 4503, you go for the input process data for the shell and the tube side fluid. In fact, this is supposed to be the data sheet with which you will start working. You require for the vapor and the liquid all the data. What all data you require? You require the thermal conductivity, viscosity, enthalpy, specific heat and density. That means if you have to calculate, you need to know how to evaluate this. It will be either in SI unit or in metric unit. The requirements, whether you require or not, they are given here. The question of vapor fraction comes only for two-phase flow, and naturally the range of dew point and the bubble point that I have said will come in case of boiling or in case of condensation. I think with this you will start your actual design work, which will be covered from the next class onwards. But let us also have a look what should be the deliverables from that particular design step. Here what we have is a filled up data sheet for a hypothetical company at Kharagpur. So it is a vapor condenser. Normally all such details are to be provided because every designer will have a particular reference, and that reference will be there depending on the order that comes. So these are the data pertaining to that information. You have a gross surface area of the exchanger. You have the surface of the shell, which is also the same. Basically it could be slightly different, it could be slightly different because you may have some special type of units. Now whenever you definitely have to find or you have to know from your design the fluid allocation, the fluid name obviously, the details of the vapor and the liquid in and out, a presence of non-condensables. The temperatures have to be there. If it is a mixture of fluids, you have to specify the dew and the bubble point. The density of the vapor and the liquid has to be there, the viscosity data. So basically what we have in this particular thing, which is the initial part of your total design output specification table, and the rest of the table is there in the next slide. Let us have a look. Here again we have the shell side and the tube side data. The pressure, velocity, pressure drop, fouling resistance, heat exchanger thing, and the construction of the cell is also given here. One thing we will note and here, that is we have the nozzles. The sizing of the nozzle normally is based on the factor rho into V square. Depending on what the velocity is and what the velocity of the what the density of the fluid is, we have a rho V square value, which from based on which we decide the nozzle size. This will come and we do later on. So with this, I think you have been given an idea that what exactly is a shell and tube exchanger, what are its general procedure for design, and finally what I have tried to give you is an idea that what should be your final deliverables of your design step, which you are going to learn next. There is only one thing beyond this, that is a fabrication drawing details, which we have not included here right now. I think I will stop here today. Thank you.